Hi friends, nice to see you today. I guess we can start
Hello.
today's
Can I
lecture.
ask a question before we
Okay, go
start?
on.
So now it is like what lecture? We have passed like 8 lectures on mathematical statistics.
Yes.
And when will we have a midterm? And how
Um,
will it be? So,
so my plan was to put the midterms somewhere closer to the end of March. As soon as we will cover the most part of mathematical statistics and we will be ready to move to machine learning. So I will let you know in advance. Don't worry.
okay, that's nice. Thank you.
Middle to the end of March, something like this. So no earlier than in 2 weeks. Don't worry about it. Anything else?
Not really.
Okay. So today we start the discussion about the essential part of econometrics, the fundamental concept, which is called a linear regression model. So my plan is to discuss the concept of this. What is this linear regression model? Why are we interested in this? And what kind of questions can we answer with the help of this linear regression model? So the whole course is going to be based on this concept. And if you understand the linear regression and if you will get this idea, so I hope that you will not have any troubles with the further material. So let's start. I hope all of you remember what we did last time on the exercise session. We explored the data set on the school districts in California, and we explored in particular two variables. One variable was the test score, average test score for the schools in the district, and the other variable was the student to teacher ratio. So given this data set, we can ask, let's say, two questions just in general. So for example, question one. So we have a municipal government and the government must decide whether to hire additional teachers. Well, they want your advice. And in particular, this question concerns two things. So first thing, if you hire the teachers, you will reduce the number of students per teacher. So you will reduce the student-teacher ratio. That's quite simple. And on the other side, we are, as economists, we care about the expenditures. So on the one hand, we reduce the number of students per teacher. On the other hand, this is somehow a benefit because we expect that the test score would increase, probably. On the other hand, we have increase in budget expenditures. Definitely, we need to know how efficient this step is going to be, right? So if the government cuts the class size, for example, by two students per teacher, what will be the effect on the student performance, right? Measured by the scores of standardized tests. Would it have the positive benefit for the student performance? The other question that we can ask, suppose there is a father and this person tells you that his family wants to move to a town with a good school system, right? So people are concerned about where to send their children, and definitely they want to know which district is the best one to live. Well, we can be interested. So for example, this person can be interested in a specific school district. So the test scores for this district are not publicly available. We don't know exactly what is the performance of students, but we know the class size based on the district student to teacher ratio. So your task can be to predict, given the district class size, what might be the test score in this district. So look, we are talking in about two conceptually different things. So one thing is related to the causal effect, right? So here we want to know what is going to be the outcome of our action. So we act in a way that we reduce the number of students per teacher by increasing the number of, by hiring additional teachers. And we want to know what is the effect on the student performance. That's one thing. And we have discussed these causal effects in the last lecture. Another type of questions is to just produce some prediction. You don't know the output, you don't know what is the test score in this district, what is the student performance, but you know the number of students per teacher, and with this help you can produce some prediction. Okay, so please try to make a distinction between these two questions. Those two are the most important questions in econometrics, and so for answering both questions, we want to know the relationship between class size and test scores, definitely, right? So we want to know how they are related to each other. Yes, as I said, in the first question, we have a situation when we want to estimate the causal effect of a change in one variable, the student to teacher ratio x, on the other test scores, which is the outcome variable y. In the second question, we need to know how x relates to y on average, right? So we want to know this to make some prediction. And as I said, these two questions are examples of two different types of questions in econometrics. So one question concerns the causal inference. So we want to use the data to estimate the effect of an outcome of interest of an intervention that changes the value of another variable. So in this case, we, as a government, we make some actions. We increase the number of teachers, and we want to know what is going to be the causal effect of our action. What exactly will be the outcome of our action? The other question is called prediction. And for making this prediction, we want to use the observed value of some variable to predict the value of another variable. So look that basically that father does not intervene the student to teacher ratio and doesn't make any change to this. So he just knows one variable and wants to produce the other one. So today we start the discussion of the linear regression model, which relates one variable x to the other y. So as you probably remember from our discussion on mathematical statistics, the whole course of econometrics concerns the relationship between variables, between one variable and the other. And this linear regression model is exactly the model that produces this relationship. The model postulates a linear relationship between x and y. And if we are talking about a linear relationship, we want to know what is the intercept. So later I will describe you what is this intercept, and we want to know what is the slope. So every line has an intercept, has two parameters, intercept and slope. Well, those two are unknown characteristics of the population joint distribution of these two variables. So if you remember at least something from statistics, I hope you remember that we devoted 3 lectures to the question of joint distributions of two variables. And so here we would need some of those concepts, at least to discuss the concept of a joint distribution. So, and in the econometrics, the main problem here is to estimate the intercept and slope. I hope you see the similarities with statistics. I hope you see that we want to produce some mathematical model that relates variables to each other, and then with the help of this model, and not with the help of this model, sorry, but with the help of the data, we want to estimate the parameters of this model. In statistics, we mostly talk about single variables, and we just came to the question of comparing two samples and comparing two distributions of two variables. And here we will always talk about joint distributions of two variables and about the estimation of the unknown parameters that characterize the relationship between these two variables. So that's our goal. So what exactly is the linear regression model? So if you want to represent mathematically the relationship between one variable, test score, and the other variable, class size, we can represent this in the following way. So who remember what is this left-hand side? How should we read this?
Dependence, like test score given class size.
But how exactly do we call this object? This E?
Conditional probability? Or
No,
E, you mean?
it's not probability. It's what? E. I just made I made it a bit like fancy E, but it's as usual E. What is E?
Expected value?
The expected value, yes. It's an expectation, and you are right, it's conditional expectation. So it's a conditional expectation of a test score given class size. So the test score is treated as the random variable, and if I know something about the class size, for example, in the second question, right? So if you know that the class size, let's say 20, what is the expected value of a test score given this class size? Exactly what we want to do. And again, you see the similarity with statistics, I hope, because in statistics we talk about the expected value itself, right? So the population mean. But now we want to calculate the conditional expectation, and the conditional expectation must be described in some functional form. For example, here we have this functional form, and this is just an equation of a line, right? So it's one parameter called intercept, beta 0, plus beta class size multiplied by the class size. So if I know all three values, I can predict, I can make a best guess of a test score in this district.
So we have this sign beta in like in the topic of type 2 errors. Is it connected somehow?
No. It has nothing to do with that beta. No.
Okay.
No, almost. So this is just a convention to denote the unknown parameters, precisely the parameters of this linear regression model in econometrics. This beta and beta from test from type 2 error has nothing to do. Yeah, so what is this? You are right, this is a conditional expectation of a test score given the known value of a class size. If I know a class size, I can predict the value of a test score, or the mean value of a test score given the class size. So beta 0 is the intercept. So this number, which is here, is called the intercept. And beta subscript class size is called the slope. So this number is a slope. And as I said, if you know beta 0 and beta class size, we can use this equation to answer the father's question, what is the expected value of test score if we know the class size? For example, if the class size is 20, if beta 0 is some number, 720, and if beta class size is minus 0.6, we just plug all these numbers into the model and we can produce a prediction of a test score in this district, which is 708. So this is our best guess. That this is what we expect. Look, now expectation looks a bit slightly differently. So in mathematical statistics, we spoke about unconditional expectation, right? So there was just expected value, mu, and it has nothing to do with another variable. So now we make one step further and we try to model how this expectation changes with the class size. If you remember several weeks ago, when we estimated the parameter lambda for the Poisson distribution of what was there, the number of transactions on the Moscow exchange with Gazprom stock. And I asked you, do you believe that this lambda is constant all the time? Well, basically lambda as an unconditional expectation is constant, so it's fully correct. But this lambda may change under different conditions. For example, if there are some special news about Gazprom, the average value of transactions may change. So if there are some positive news or negative news, the trade is going to occur frequently. If there are no news, so probably the trade is gonna be less frequent. And that's exactly what we want to do here. We want to produce not the unconditional expectation of a test score. So we want to know how this expectation depends on the other variable, on the class size. So conceptually, that's, as I said, that's a step further. We are trying to decompose this expectation with the help of the relationship with other variables. So there is a very important concept in econometrics called the error term. So this equation from the previous slide shows the average level of test score given the class size. So we are talking just about the average, but the precise or specific test score in the district, this equation is not able to describe, right? Because this is the line, and definitely not all the districts belong to this line. Therefore, we rewrite this model slightly, and we introduce this in the following way. So the districts with the same class sizes, so with the same number here, they can differ in other characteristics, and they will have different values of test scores. This must be understood because, well, maybe these districts have different income of people, and the district with richer families, for example, may produce higher test scores. The districts with the larger number of migrants, for example, can produce lower test scores. So other factors may also influence the differences in test scores. The class size is not the only one that makes this. And everybody must understand this idea right from the beginning. So even though we are interested in the effect of a particular variable, class size, on the other variable test score, there are many more factors that influence the same outcome variable test score. And therefore, the prediction will not be exact, right? So that's going to be just some average expected value. In order to make this model mathematically precise, we introduce the concept of an error. And this error mathematically will look like this. So the exact test score in the district. Look, not the expectation, but the exact number, the exact test score equals to beta 0 plus beta class size multiplied by the class size, which is this part, right? And plus the error. So plus the deviation from our expectation. So this deviation might be positive, negative, but look, this deviation occurs because of the other factors that can influence the same outcome variable test score. That's an idea. So let's try to formally introduce this linear regression model. So suppose we have a sample of n districts. So in our data that we have discussed on the exercise session, we had 420 districts. So let's denote yi, the average test score in the ith district. So xi will be the average class size in ith district. So now this equation from the slide 4 becomes, so the conditional expectation becomes this equation. So instead of beta class size, we just count this as beta 1. So the conditional expectation of yi given xi equals to this. And this is the regression line. So we denote the error with ui, and this error is made by the prediction yi using the conditional mean. So here the equation from slide 5 becomes this. So yi, the exact value of y, equals to beta 0 plus beta 1 xi plus ui. For each district, I from 1 to n. And we call beta 0 the intercept, and beta 1 is the slope. And we need to introduce some terminology. So this terminology is gonna be used throughout the whole course. So please try to go through this after the lecture and try to make yourself familiar to this terminology. So we have the linear regression model with one regressor here. So the subscript I usually runs over observations from 1 to n. So yi is called the dependent variable, or sometimes you can find such names as regressant or the left-hand side variable. So all these terms are the same. Those are synonyms, and you can see all of them in the literature related to the econometrics. So xi is called the independent variable, the regressor, or the right-hand side variable. So this part, beta 0 plus beta 1 xi, so the conditional expectation. So this part is called the population regression line, or the population regression function. So remember the concept of population from statistics. So we are talking about the linear relationship between x and y in the population. So for all school districts, this relationship must hold. This is something like those unknown parameters from mathematical statistics that we have discussed, like mu, lambda, sigma, and all the other parameters that we have discussed. So this is exactly the same. So we don't know beta 0, we don't know beta 1, but we formally, mathematically believe that y and x are related in this way. So beta 0 is called the intercept of the population regression line, beta 1 is called the slope of the population regression line, and ui is the error term. So all these terms are necessary to remember what is what and how do we call every part of this model. Why? Because throughout the course we will use all these terms every time. So regarding the population parameters, so what these parameters, why are we interested with these parameters, and what these beta 0 and beta 1 tell us precisely? So as we discussed, the population regression line holds between y and x on average over the population, right? So it must be applied to any school district, not only to the districts in our sample. We believe that there is such a relationship between x and y. So the intercept and slope are called the coefficients or the parameters of the population regression line. The same term as we use in mathematical statistics, parameters or known parameters of the model. So what is the slope? What does beta 1 tell us about x and y? So beta 1 is the difference in y associated with a unit difference in x. So if x changes by 1 unit, y changes by beta 1. I hope this is clear, right? So if I change x, for example, if I increase x by 1, then y will change by beta 1. So what is the intercept? Sometimes people are confused with the meaning of intercept. So the intercept is the value of the population regression line when x equals 0. So go back here. If you plug x to 0, if you plug 0 instead of x, sorry, then this part becomes just beta 0, right? And beta 0 is the expectation of y when x is 0. And here is the trick. So graphically, the intercept is the point at which the population regression line intersects the y-axis. That's graphically. And you will see the graph and you will understand what is beta 0. But practically and economically, the thing is that sometimes the intercept does not have a meaningful economic interpretation. So we cannot interpret what is beta 0 in relation to x and y. For example, in our case, when x is a class size, the intercept is the expected value of test scores when there are no students in the class. When there is 0 students per teacher, beta 0 is the test score or expected test score. So definitely it is nonsense. We cannot tell that any district may have 0 students and yet has some test scores. Therefore, beta 0 usually serves as the formal mathematical parameter just to produce this regression line. But most of the time we are interested in beta 1, in the slope. Why? Because this slope helps us to predict what? Helps us to predict the causal effect of changing in x on y. If we increase or if we increase the number of teachers by 2, what is gonna be the change in the test score, let's say. So beta 1 helps us to predict this causal effect. Well, as I said, when the real-world meaning of the intercept is nonsensical, it is the best to think of it simply as a coefficient that determines the level of the regression line. Just a formal mathematical parameter, nothing else. No economic interpretation. And that's gonna usually hold in many of our applications. So beta 0 will not have any particular meaning. So now let's see graphically what are we talking about? So this graph is taken from the book. And what do we have here? So look, each point here, 1, 2, 3, 4, 5, 6, 7 points, represents the pair of numbers x, y, and y1. So x is a student to teacher ratio, y is a test score. So for example, one district has 15 students per teacher, and this district has something like 680 points as a test score. This is one district. Another district may be located here, so this district has something like 17 students per teacher and 640 as a class size. The third district is here. It has something like 18 students per teacher and 670 points, and so on. So every point here shows us a particular district and the combination of these two variables, student to teacher ratio and test score. And you see that there is no precise linear relationship between them. So here, kind of through these points, we draw this population regression line, which is beta 0 plus beta 1x. So this line shows the average relationship between x and y, not the exact one, but on average. So we see that on average, when the student to teacher ratio increases, the test score goes down with the help of this line. So if we extrapolate this line to the left, so somewhere this line will cross the vertical axis, and the point on the vertical axis where this line crosses it is beta 0. So beta 1 shows us the slope, how steep is the slope of this line. And what is the error term? The error term is a deviation of, so the vertical deviation.
Sorry, again, intercept is when this line crosses like vertical
Axis, yes.
axis, yes, and slope is?
Slope measures how steep is this line. So the
okay.
angle of this line. So basically, the slope is just a synonym of an angle. So it's either like very steep and goes down, or flat, or goes positive, increases or decreases, and something like this. So that's the meaning of beta 1. So just try to refresh your memory from the basic mathematics in school. What is the equation for a line and how these two parameters describe this line.
And it is regarding the bottom axis, right?
Like what regards the bottom axis?
Oh, okay. Like, never mind. Just an angle. I get it. Thank you.
Yes, it's just an angle. Just an angle. Yes, angle related to the horizontal axis, definitely. Yes. So beta 1 describes you how steep is this line with regards to the horizontal axis. So the error term, where is the error term? So the error term is a vertical distance from the of the actual point from the regression line. So you see that the line is located here, and the actual observation sometimes exceeds your prediction, sometimes it is below your prediction. So this is the error term. For example, the first error term is positive, and the second error term is negative, right? So the actual y2 is below what is predicted with the help of this line, and so on. So for these 3 points, we also have positive error terms. For these, we have negative error terms. So this is the visual representation of what we have discussed on the previous slides. How simply we can represent all these relations and all these variables on one graph, and how we can, with the help, discuss those 2 questions that we posed in the beginning of our lecture. So now the question is how to estimate these coefficients. So the population parameters beta 0 and beta 1 are unknown. We don't know what are these beta 0, what is the beta 1. The procedure of estimation has been discussed in the mathematical statistics course. I hope all of you already remember and understand that in order to estimate the unknown parameters for the variables and for the probability distributions, we need to do the following. We need to collect the data, right? So we must use the data to estimate the unknown coefficients. And the precise idea of estimation has been discussed there. So the whole thing is going to be exactly similar to what we had on the statistics course. So we are already familiar to the data. We have seen this on the exercise session. This is the data from 1999 for 420 California school districts that serve kindergarten through 8th grade. And the test score, the dependent variable, is the district-wide average of reading and math scores for 5th graders. We also discussed the meaning of this number. So what is the exact metric used for this variable? And the class size. The class size can be measured in different ways, right? So in this particular example, we will use the number of students divided by the number of teachers, so student to teacher ratio. Please be careful that usually what are we talking about right now is the following. So we stated some idea, or we stated some hypothesis, right? So that a test score or the performance of students depends on the number of students, or depends on the class size. That was our initial working idea. And this is somehow reasonable. And we, first of all, we try to summarize our beliefs, how these two variables depend on each other. And then we try to come up with some measurable metrics that we can use in order to estimate the unknown parameters. Because how should we measure the performance of a class? In a way that all the classes are comparable. So luckily we have this standardized test that is given to all students in all districts. The next question is, how should we measure the class size? So we can just calculate what is the average number of students in the class. That's one way of calculating this. But maybe this is not the best one. We can calculate, as here, the students to teacher ratio. So how many students per one teacher do we have in the class? Maybe there are some other metrics. So please be careful that in the practical applications, there is no one way to measure something, because you start with the conceptual idea, you start with just some question, well, how this is related to this, how the performance is related to the class size. And then you are coming with some measurable or observable variables that can be used reasonably in your research. That's quite important. So we have seen this table. We basically produced ourselves this table on the exercise session. Just let's refresh. What do we have in this data? We have the average student to teacher ratio 19.6. We have the average test score 654.2. We have the respective standard deviations, and we have some distribution which is given by the percentiles. So we have discussed how to read this table. Just let me remind you that, well, yes, the average is here, the standard deviation is here. What these percentiles mean, that the 10th percentile of the distribution, 17.3, which means that only 10% of districts have student to teacher ratios below 17.3. right? So everything, so out of the whole sample, 420 districts, so 10% of 42 districts, I have class sizes which are less than or lower than 17.3. The quarter of districts have number of students per teacher less than or equal to 18.6, and so on. Yes, and 19th percentile, 90th percentile, 21.9, which means that the let's say that 10% of districts have the number of students per teacher greater than or equal to 21.9, right? So I'm looking to the right area from this point. So the meaning of these percentiles is the same as from probability, but please be careful that we are talking about empirical percentiles, and I was drawing your attention during the exercise session. So these percentiles are not percentiles from the probability distribution. These percentiles are percentiles from the empirical distribution of these variables. This is quite important to understand. So now, based on the data, we can produce something which is called a scatter plot. So several slides before, we have seen the scatter plot for 7, districts. So now this is a scatter plot for all 420 districts. And as I said, every point here, every point on this graph describes or illustrates the particular district. So for example, this left top point means that one district has the student-teacher ratio around 15, right? So slightly less than 15, and very high test score around 695 probably, right? So there is the huge test score here, more than 700, for the district where the average student-to-teacher ratio is 18, and so on. So we see that the kind of the concentration of the most of the districts occurs here in the center, and some districts are located just out of this, let's say, of this concentration. So what can we see from this scatter plot? Is there any relationship between student-to-teacher ratio and the test score in the data? So do we see, let's say, positive or negative relationship? Do we see that increasing the student-to-teacher ratio leads to the decrease in test scores?
Not really.
Not really. That's true. Well, basically, it's hard to say because the dispersion of these points is quite large, right? So these points are distributed across the field in kind of in chaotic manner. But still we see that when student-to-teacher ratio increases, so the test scores, at least large test scores, disappear. So on this upper border, we see that, well, some negative relationship occurs. And also on this lower border, we also see that, well, even if the student-to-teacher ratio is low, and there are some, let's say, outsiders, right? So like the district with very low test score, but still these lowest test scores go down. And probably there is some weak but negative relationship between these two variables. So we don't know, and that's exactly our question. Is there any relationship between them? So another graph that I have produced that might be potentially difficult to comprehend, but basically, so let me describe this graph because it gives us a lot of information. So let me start with these borders on top and on the right. So these borders are the let's say the densities of the respective variables. So we have the student to teacher ratio. You remember that we have drawn the histograms on the exercise session, and we discussed that the histogram is something like the probability mass function. And if you make it smooth, so the probability mass function becomes the probability density function. So on top, we have the empirical probability density function for the student to teacher ratio. And we see that it resembles somehow the normal distribution, like this looks like a bell. On the right, we have the same, we have the density plot for the test score. And this density plot, well, it's a bit far from normal distribution, but still it looks like a bell with the slight, let's say, with a slight deviation here. Sorry, what?
I said it's a damaged well.
Yes, it's a bit damaged, but okay, so we are working with the real data. There is nothing ideal in the real data, and we want to find such a data that at least close to being normal or close to being approximated with all those models. So in the real life, there is nothing ideal. So what is in the center? In the center, we see the joint distribution of these two variables. So first of all, this plot resembles the scatter plot, and the plot that we see here shows us the density of these points of the scatter plot for every pair of coordinates str and test score. So you see that the most dense, let's say, of these points are concentrated densely in the center, and that's exactly we see here. If you remember something from geography, and if you are familiar to the maps of like physical maps of a land, you know that sometimes, or not sometimes, so usually, the mountains are represented with these lines, and every line basically shows us the height of this mountain. So the top is here in the center, and the bottom is here, where this contour shows us the wider, let's say, border. So this is the mountain which we observe from the top, and these two are just the projections of this mountain. So this is the projection of our mountain when we see this, when we look this from the side of STR, from, let's say, from the left. And this is the projection of this mountain when we look at this mountain from the other side, right? So for those of you who are familiar to this, like 3D modeling, this picture must be also must let's say deliver an important information about this. And look what else do we see? We see that this mountain is slightly how to say, this mountain is slightly goes from the top left to the bottom right. So it's not ideally circle, right? So it's not an ideal circle. It is somehow stretched from left top to the bottom right. And this stretch of this mountain shows us exactly that there is some weak but negative relationship between STR and test score. So we can see this with the help of a scatter plot, that's totally fine, but also we can see this with the help of this joint distribution plot. And whenever this mountain observed from the top is going to be stretched more and more, kind of from left top to the right bottom, we can see that the relationship between STR and test score is stronger and stronger. So we will see with you several other examples on the exercise session, how else we can use this plot in order to verify that there is some relationship. But as I said, from this graph, we can see a lot of information. So first of all, we can check whether both variables can be approximated with the normal distribution. And the other thing that we can check here is if there is some relationship between these two variables, and this relationship can be shown if this central graph does not look like an ideal circle, but instead of this, it is, let's say, it is closer to being elliptical. So it is stretched from one side to the other side. In this case, there is some relationship between two variables. So, okay, some explanation of what we have seen. So the scatter plot of the 420 observations indicates, as we said, a weak negative relationship between the two variables. So there is no strong and close to being linear relationship, but still there is some weak negative relation. So larger classes in the sample tend to have lower test scores on average. But the fact that there is a wide dispersion of the points indicates that there are other determinants of test score that keep the observations from falling perfectly along a straight line. So the other effects, the error terms that we have discussed before, influence the test score in a way that it deviates from laying on the straight line. They deviates far from this line. If this scatter plot would be kind of concentrated around, along the line, then we would claim that the other terms influence the test score not that much. So what is our task now? Our task is to draw a straight line through this data, through these points, like we had here. So we had this population regression line. So our task now is to draw the estimate of this population regression line, because we don't know what is beta 0 and what is beta 1. We have no idea about this. And we want to find out with the help of this data. We want to estimate beta 0 and beta 1. That's our first step. And then we want to draw this line through these points. That's our task. That's our goal.
Can we go back to some slides? And
which one?
And some more, but with the graph.
This one.
Yes, please. Isn't X class size? I see.
Yeah, it's a class size measured with the help of student-to-teacher ratio.
Yeah, okay, I see, yes.
Those two are just the same.
Yes, thank you.
Okay, so we have this data, we have the scatter plot. So our goal is to draw a straight line through this data. And the slope of this line would be an estimate of beta that we wanted to know. And why do we want to know this beta? Because with the help of beta, we can predict what would be the effect of the class size reduction on the test score. And with the help of the whole regression line, we can predict what would be the test score given the class size. So the problem is that we can draw a lot of lines through this scatter plot. How should we choose among these many possible lines? And the procedure to choose is called the ordinary least squares, and it produces the ordinary least squares estimator, or simply OLS estimator. So you know from mathematical statistics method of moments estimator, you know from mathematical statistics maximum likelihood estimator. So we will introduce in econometrics another class of estimators, which is called OLS estimators. So precisely to understand this problem, look, we have this scatter plot, and in principle we can draw many different lines through this scatter plot. Well, the question is, which line fits better? Which line is the best possible estimator for that population line, beta 0 plus beta 1 times x, that we are looking for? Well, seems like all these lines more or less nice and more or less fit the data. Well, basically I could draw, like, you see that all of them go through the same point, but basically we can draw some other lines, and that would be totally fine. Yes, and this task we will start in the next lecture. So we will start the discussion of the method of ordinary least squares, which is just another method of estimation. So we know the method of moments, we have the method of maximum likelihood, and we will introduce the method of ordinary least squares in order to produce the estimate of this population regression line. So I decided not to start this topic today because it's quite complicated. It needs from you the necessary attention. On the next exercise session, we will discuss some necessary, let's say, theory, and we will practice some tasks that will help you to understand ordinary least squares better. One additional thing, that tomorrow you will have the quiz number 2, which is going to be based on this lecture. So this quiz is going to be somehow similar to the quiz that we had, that bonus quiz on mathematical statistics. That's going to have true or false questions, open questions, multiple choice questions, related to what we had today, related to the terminology, simple calculations, like assume that you have the parameters, what would be the prediction of the outcome variable. Well, everything is going to be based on this lecture.
And this will be the same as the bonus quiz.
I mean, the structure of this quiz is going to be the same as the bonus quiz from mathematical statistics, but this quiz is going to be counted in your final grade, definitely.
Why is it only like one day then?
Well, it's going to be short. 5 questions, 5 points.
Okay, and exactly on this lecture, right?
Yes. Yes.
Okay.
Everything from here. Questions? Looks like today we are ready to finish earlier.
That's good. You always say.
Well, if there are no questions, then that's all from me for today, and see you next Thursday for statistics.
But what calculations then there will be with?
Like this, something.
Like this one. Oh, okay. That's nice.
Yeah. Anything else?
No.
Okay, perfect. Then have a nice weekend. I guess tomorrow you have the working day, so that's why I have decided to put this quiz tomorrow. And then you have three holidays, 3 days of holidays,
No.
right? No. Yeah, you study on Monday. Yeah, I know.
Yeah.
So then I'm sorry for you. Still, see you on Thursday.
Bye-bye.
Bye-bye.